For those of you online, I'm not sharing my screen yet, just in case you're wondering why you can't see anything. We'll do it here in just a moment. Any questions while we wait just a few more moments for people who might be walking in from their remote parking spot? Okay. Yes, they are. Okay, so were you not pre-registered?
I was. I mean, it was on my schedule.
Okay, so you had to go in and actually submit your email address to a registration link. So if you didn't do that, you probably were not on any of the emails that got the materials. Come find me right after. Did you email me actually? Yeah, I thought so. I've gotten a couple of emails about this. I've been forwarding them to my the person who manages the stat education mailbox, but she's been in and out this week. So come find me right after this, and I'll make sure that I forward you the documents. Let's see. Hi. Is this screen okay, projection-wise? Oops. Is that better? Okay, I'm going to go ahead and get started, even though people might trickle in. In this third week, we're going to start talking about specific methods. And I'm going to focus on probably the methods that you read more frequently in the literature, and maybe that you could even perform on your own if you're comfortable with a statistical analysis tool like SPSS or SAS or R. That's not to say that this is a comprehensive look at all statistical methods, because as we'll see in a moment, there are probably an infinite number of models that you could apply to your data. The model should just reflect the design and how the data was captured. But we're going to talk today about statistical methods for comparing groups, because we often have some kind of standard of care or control group, and we want to see how this new experimental intervention or treatment or drug performs relative to what's currently being used. Next week, we're going to talk more about regression methods. So we're going to introduce the idea of regression today, but we'll focus mainly on regression methods next week. And when I say regression methods, I mean regression for any kind of an outcome. So the biggest question, aside from how many subjects do I need for my study in order to be adequately powered, is what statistical test do I need to use to answer this question, given the kind of data that I have. And so I like to make sure that everyone understands that it's not a straightforward answer. It really is highly dependent upon everything that's happened prior to the data being collected. And it's actually even dependent upon the data collection itself. So if we recall all of the things that we talked about in the first 2 weeks with regards to experimental design, thinking about sources of variation in the outcome, and then what type of outcome is it? And then what kind of research question are you actually trying to address? All of those things play a role in deciding what statistical test is appropriate to address the research question. So again, what is the research question? What was the study design? Was it an observational, like a cross-sectional study? Was it a randomized controlled trial? Was it at a single time point? Was it longitudinal? Are there repeated measures on individuals? Is it pre-post? All of those kinds of things play into the selection of the statistical method. So you can see very quickly it can become complicated. I do like to show you all kind of a hierarchy, a rubric, if you will, of how do I select the right test. But it's kind of rudimentary in the fact that it can't possibly account for all combinations of these things. So for today, for the moment, we're going to assume kind of the simplest version of an experiment where I'm just looking at an outcome on subjects. And I want to compare that outcome between subjects who receive different kinds of treatments. So it's not longitudinal, there's no repeated measurements. We don't have things that we're adjusting for necessarily. What we're going to focus on today are the methods that are appropriate depending on what kind of outcome it is. So is it continuous? So are you measuring reduction in blood pressure or reduction in weight or something like that? Or is it categorical, like did the patient respond to therapy or not? And that will be kind of the primary factor in our rubric for determining what test is appropriate. So again, when you're thinking about the test that you use, the research question, the study design, what is the type of outcome? In past years, I have actually explicitly defined the different kinds of outcomes that you can have in a study. And when I mean define it, I mean I go through the levels of measurement. Has anyone here ever heard of the term levels of measurement? No. I've not gone over that in the last 2 years because I feel like we kind of waste time going over something that you could Google really quickly. So I encourage you to Google levels of measurement. What levels of measurement indicates, it indicates how much information is actually contained in a measurement. So something that's nominal only indicates difference between individuals. So can someone give me a variable, a measurement that I could take on an individual that would indicate that they are different in some way from another individual? Just give me a measure.
Blood type.
Blood type, perfect. Nominal, right? Only that they're different, not that one's better or worse than the other. Someone else said something else. Gender, sex, race. Is it pretty clear what nominal is? So if I say female gender, I indicate that that individual is different from someone with male gender, but I don't indicate one is better or worse than the other. So that's the least amount of information you can get from a measurement. We tend to not want to work with a nominal variable if there is a more informative measure of what you're after. And we also tend to not like to take variables that have more information and remove information from them. For instance, measuring something continuously in a continuous fashion, like age, and then, or not measuring something continuously that could be measured that way. So I see a lot of times in surveys that are developed, whenever you're asking a person's age, they'll say, well, are you between the age, are you under 18? Are you between 19 and 25? Why are you measuring it that way? Because you may have two individuals. It's kind of an arbitrary selection of categories. Measure their age in units, specific units like years. And then if you want to, after the fact, you can always go from more informative to less informative. You can categorize those yourselves when you're creating the figures and the tables. So if you can measure something, measure it in the most informative way possible. Ordinal is only different from nominal in that it indicates both difference and also there's some kind of inherent order in the categories. So can anyone give me an ordinal variable where you are indicating that two individuals are different, but the measurement itself, the numeric measurement, indicates that there's some ordering of those particular characteristics? Old and young, yeah. So if you measured age in old and young, that would definitely be an ordinal measurement. What about like classification in college? Freshman, sophomore, junior, senior, right? It's a classification variable where we know that freshmen are kind of earlier in the process than seniors. The differentiation between an ordinal variable and something that's more informative is that though we do know that different categories are higher or lower in terms of the relationship, freshman is earlier than senior, for instance, we don't have a specific way of quantifying the difference between a freshman and a senior. Because if you have a freshman and a senior over here, Joe and Casey over here, one may be a freshman, one may be a senior, but there might be, let's say, 100 credit hours difference between their experience. And if you get two other individuals, Bob and Bill over here, freshman and senior also, there may only be, I don't know, this might be incorrect, 60 credit hours different between them. So measuring something in an ordinal fashion does give you the order, but it doesn't tell you how different they are. Another example I like to give of ordinal variables is sports rankings. I give this every year. So everyone here's, we're at KU, right? KU's pretty good at basketball. I always joke about if we're looking at our conference, maybe we're number one and I'm not trying to think of who's been good recently. Who's been good recently in the Big 12 besides Kansas? Who won it last year that knocked us off? I can't even remember. Isn't that terrible? We don't need to dwell on it. Oh, come on. It's okay. We're getting better, right? Let's say Texas Tech. I can't remember who it was. Was it Texas Tech? Was it? Somebody's shaking their head yes. So let's say going in this year, Texas Tech is still as good as they were last year and we're better than we were. So maybe the coaches vote and KU and Texas Tech are 1 and 2. But for all intents and purposes, maybe they could kind of be flipped because there's very little difference between 1 and 2. Let's say, who's number 3? Oklahoma. And Oklahoma may be way down here. I don't know if they are or not because I don't know. I didn't follow basketball last year because we weren't that good. Not terrible. So it might be 1 and 2 way up here and Oklahoma way down here, number 3. So even though there's only a 1 unit difference between Kansas, Texas Tech, and Oklahoma, the difference between 1 and 2 is very different than the difference between 2 and 3. So that is a feature of an ordinal variable where we don't really want to talk about differences. We just want to talk about order or ranking, if you will. So anything ranking falls in the ordinal category. Another example that we see oftentimes is the concept of a Likert scale. Is everyone here familiar with the term Likert scale? 1 and 5 are kind of meaningful, right? I strongly agree, I strongly disagree. But that's highly dependent on the person's perception of agreement and disagreement. So we steer away from giving a lot of meaning to like a 3 or a 2 or a 4, because my 4 could be your 5, for instance. And then interval goes from, it takes an ordinal variable and gives meaning to the differences between those ordered categorical things. So an interval variable could be temperature. Temperature is a good ordinal variable. So if I go from 20 degrees to 40 degrees, 20 and 40 are different. 40 is higher than 20. And there's a 20 unit difference that's measurable between those two. And that 20 unit difference is the same whether it occurs between 20 and 40 or between 40 and 60 or between 60 and 80. So that the intervals are meaningful, whereas in an ordinal variable, they're not. And the reason why I give temperature in Celsius or Fahrenheit as an interval variable is to distinguish interval variables from ratio variables, which are the most informative variables that we can have, because not only do they have difference and order and meaningful intervals, they also have a meaningful zero. So can someone give me a measurement that you could measure on a subject in a clinical trial where if I measure 0, that means a lack or an absence of that characteristic? Kelvin temperature, yeah. So if we get scientific, hopefully we don't have a patient with a Kelvin temperature of 0, right? But that's exactly right. That's exactly right. Anything with an absolute 0. What else could we be measuring? If I'm doing like an intervention that's physical therapy, what do we often measure for an individual, or even pain scales? Probably more ordinal, but I guess a 0 could be, but my 0 might be different than your 0, right? Muscle strength, if they can't move something at all, then there's a lack of. What about like distance walked, or the time it took to complete a task? Because 0 means nothing, right? So anything that's time, distance, production. When I say production, I kind of mean some of these tests where they have to do something repeatedly until they tire. Even if we think about labs, blood draws, or something like that, it might be below some kind of detectable limit but for us, that's kind of a 0, right? So if you have a 0, then a true 0, that indicates that you have a ratio variable. And why do we differentiate between interval and ratio? Because of the way we like to describe things between groups. For an interval variable, I probably only want to talk about differences between them. So group A's, outcome is 4 units higher than group B's. But if I have a ratio, I can talk about fold change. Because the 0 is meaningful, then I can talk about, for instance, in survival, we give hazard ratios. Because 0 in survival is meaningful, right? There was no time lapsed before death. And so a 1.1 ratio indicates a 10% increase in survival associated with something. And that's why ratio variables, you have to be careful because you don't want to talk about interval variables in terms of ratios. So that's my spiel about, I probably could have just not talked about that, but I think it's helpful to lay the framework to make you recognize that you should be thinking about what information is actually in your measurement. Not only in the selection of the measurement, can I get something closer to an interval or a ratio? If not, then nominal is fine, ordinal is fine. But if you can get something more informative, always capture it, because you can always remove information from it by classifying it, for instance. But you can never add information back once you've measured it at a lower level. How many samples are you comparing? So, for instance, this is a function of your design. How many treatment groups? Is it pre-post? Is it longitudinal? That kind of thing. And then are your samples related? Are they made up of individuals that are totally independent from one another? Are they paired in some way? or do you perhaps have repeated measurements? And then what is your sample size? The reason why the sample size is important, as we'll see in a moment, is that all the methods that we tend to use, the t-test, ANOVA, chi-square, linear regression, logistic regression, survival analysis, they have assumptions that we have to verify before we just plug and chug and report the results. If you don't verify assumptions, you can still get R or SPSS or SAS to produce p-values and effect sizes, but they will not be what you think they are. They won't be the real p-value. They won't be the true effect size or a valid effect size measure, because all of these things are developed using mathematical principles that require you to state an assumption about the behavior of the data. If the data doesn't behave that way, then the method is not, it's not performing the way that it was designed to perform. So sample size is important because you have to have enough data to be able to at least say reasonably that these assumptions are met. So what if we have, and again I mentioned the thing that we're going to differentiate methods between today is really what kind of measurement are you taking. We're going to assume it's really simple, no longitudinal measuring, just a single outcome. And then we're going to focus on how many groups are you trying to compare this outcome across. So if you have a single continuous dependent variable, when I say continuous, I'm talking about interval ratio type data, not ordinal. A single continuous dependent variable, so BMI, weight change, blood pressure. Other examples? Anybody have specific examples from your field of measurements that are important that might be continuous? Interval or ratio? Time to complete a task, survival, time, counts, even counts sometimes. We'll show counts often don't meet the assumptions of these methods, but so those kinds of variables are usually analyzed using a combination of the methods that you see here on the right. If your dependent variable, which is the outcome of treatment, is dependent and you only have a single group of individuals, and you're measuring that outcome, then you do a one sample t-test, making some assumptions that need to be valid. We'll talk about what would you do in case those assumptions are not met, and what are those assumptions. If you have two treatment groups or two risk groups or two cohorts or something that categorizes your data into two independent groups, and you're comparing that continuous dependent variable between the two, that's a two sample t-test, two independent samples. You could do, if you had repeated measures, a t-test as well, like in a pre-post fashion, but we're not talking about that here. If you had three or more groups, you don't do multiple t-tests. You do what's called analysis of variance, which basically functions like doing multiple t-tests, only it does it in a way that produces valid estimates of the effect while controlling the type 1 error rate. In other words, if you do multiple t-tests, you're more likely to find something that isn't there because you're inflating the false positive rate. ANOVA controls for that. And that's again for groups here, 2 levels and 3 levels. What if the independent variable is not a grouping? So you're outside of like a randomized controlled trial. Maybe now you have a cohort of individuals and you're looking for associations between a continuous risk factor and a continuous outcome. In that case, correlation will work, or depending on the needs of the study, simple linear regression. If you have more than 2 predictors or risk factors that are both continuous, you could do what's called multiple linear regression, and it's just linear regression with multiple x's. If you have a mixture of continuous and categorical predictors, continuous and categorical independent variables, and you want to build a model, you can still do multiple linear regression. You could also, depending on what your research question, do something called analysis of covariance, which is a really specific kind of method It's just a linear regression model that allows us to compare groups while adjusting for continuous confounders. If you have still a single continuous dependent variable, you know, blood pressure change, those kinds of things, and you want to try to perform these tests in a statistical software, then I'm giving you the RStudio function here. So just a t-test is just t.test, and you'll have to put in some information in the parentheses, but it will produce the results for you and also allow you to check the assumptions. Same thing for ANOVA, correlation, and linear regression. I'm not going to spend time today actually performing this because I know that there's a variety of tools that you all use that might even be specific to your field. Just know that if you pull up RStudio, this is the function that would produce the results. The biggest thing to take home from this page, though, are the assumptions that you have to check. Notice these are the things that are required in order for the t-test to produce a t-test statistic and a valid p-value. Same thing for ANOVA, for correlation, and for linear regression. So let's go over what do we mean by normality, equal variances, linear relationship, and this big word, homoscedasticity. So normality, everyone knows what normality means, right? That nice bell-shaped curve. When we say normality, we basically mean that there's not one or two or a fraction of the subjects who are highly unusual in terms of their outcomes from the rest of the data. So you don't have outliers that are out beyond those tails. And you also have symmetry in responses. So there's some kind of average response, and then people deviate from that average in both directions. If they don't deviate in a nice way, kind of symmetric way in both directions, the t-test really doesn't perform all that well. I will say it's better to have some violation of normality than it is to have violation of the equal group variance. It's kind of robust, if you will, to normality, but it's not robust to having, if you're comparing groups, one group with very little variation in their in the subject outcomes and the other group to have a lot of variation in the subject outcomes. What happens there is the t-test could throw a false positive simply as a function of that difference in variation as opposed to differences in the means. So you have to be careful with the group variances. And I'll give you some rules of thumb about how do we do that. There's an actual statistical test to do that, but you can also just use a rule of thumb where you look at the group variances and take a ratio of them to see if they're different. And I mentioned earlier the ANOVA is doing the t. It's basically doing a t-test, multiple t-tests within a single framework, so the assumptions are the same. Check for normality. And when I say normality, I mean normality kind of within the group, within a group, not across all the groups that you're comparing, because you might see multiple distributions. And then equal group variances. For Pearson correlation, normality is still necessary. So is equal variances, only we call it homoscedasticity now because there's not really groups that you're comparing. So homoscedasticity just means that if I'm correlating an X with a Y, and we'll talk about this in detail later, then what I see is a nice elliptical pattern of data. I don't see a funnel where, for instance, for small values of X, I have very little variation in Y, but as X increases, it cones out. Should go cone that way, cones out, meaning that as X is increasing, the variation in Y is increasing. You can get incorrect estimates of the association if you don't have that nice ellipse or just a circle of data which indicates that there's really no relationship at all. And then the other assumption that's very easy to visualize is just the fact that the relationship needs to be able to be described using a line. That's what Pearson's correlation is doing. It's like simple linear regression. You could have a really strong relationship that's not linear, right? It could be curvilinear. It could come up and asymptote. It could come up and go back down and go back up again. So if it doesn't look like when you plot the data in a scatter plot that a line would describe it, you need to steer clear of Pearson's correlation because it will give you incorrect measures of the association. And then linear regression, which is in the same kind of category as Pearson correlation here. Notice you have the same assumptions: normality, linear relationship, homoscedasticity. The assumption of independence has to do with you dealing with a random sample. You're not doing repeated measurements and trying to throw them into a single plot. I made a note down here that these are all called parametric assumptions or parametric approaches. If a method is parametric, that means it's going to have some pretty rigorous assumptions that need to be verified before you know for sure it's producing valid results. If you can either not verify the assumptions because you don't have enough data, let's say you have 10 subjects and you do a histogram to just see, does it look normal? It's pretty hard to tell with just 10 observations if you've got normality or not. So in that case, small samples where it's hard to verify the assumptions of normality, equal variance, linearity, whatever, or if you have a large sample but the assumptions obviously are not valid. Maybe you have unequal variances in your groups. Maybe you have that cone shape in your scatter plot where it looks like variation in y is increasing as x is increasing. Whatever the evaluation is, you probably should call a statistician, I would say, because there might be some things that you can do to adjust the data to make the t-test work if you really need the t-test output, because sometimes it's more informative. But if you move the data around too much, when I say move the data, I mean take transformations or things like that, sometimes you can lose meaning. Meaning it's kind of hard to interpret whenever I say, well, I took the log of the outcome and then I took the inverse of that, and now all of a sudden my assumptions are met, but how do I produce an effect size from that? So it's kind of a decision-making process, whether or not to continue trying to massage the data to get it to fit the method, or should I abandon parametric methods and go to something called non-parametric methods. And you've probably read some of these names in the literature. In particular, you probably have heard of Mann-Whitney. I think Mann-Whitney is pretty common because the t-test is pretty common. The Mann-Whitney test is like a t-test, only it's stripped away. It's taken that continuous either interval or ratio variable and kind of made it ordinal, because it converts the raw data into ranks and then performs basically a t-test on it. So the downside to a non-parametric test in general is that you do lose information by stripping away the raw value of the outcome and replacing it with its rank. But the benefit is you get a valid result. It's a little more conservative, meaning it's less likely to find a difference, again, because of the stripping away of some of the information. But it's also less likely to produce a false positive finding, which is usually the concern when you have a parametric method whose assumptions are not verified. So I've given you a couple of examples. The ones that I commonly apply are the Mann-Whitney, because I think t-tests are pretty common. The Kruskal-Wallis is like a non-parametric ANOVA. It will compare the averages across multiple groups, but again, as a function of their ranks. Spearman correlation is the counterpart to Pearson correlation. So it doesn't require a linear relationship because it's doing a correlation on the ranks of X and Y as opposed to the raw values. And then we have some specific adjustments to regression models that I won't talk about too much, but just know that these adjustments to the regression models are specific for violations of unequal variances, the homoscedasticity assumption. The weighted least squares regression helps with that. The other ones at the bottom are kind of robust when you have outlying observations or potentially skewness in the data. So you have violations of normality, if you will. And I put a star here because you probably don't want to do weighted least squares regression or low S or ridge or robust regression on your own. I think you're perfectly capable without rigorous training of doing the sign. In fact, I would be more comfortable with a Mann-Whitney test than I would a t-test, because I know that there aren't really assumptions for the Mann-Whitney test, so it doesn't matter if you checked them or not. But the t-test, we do oftentimes see that researchers perform a t-test but don't ever take a look at the data to make sure that it's got the normality and the equivariance assumption met. But I would steer clear of these. If you need help, you can call a statistician, either one that you all know personally or someone here, and we can walk you through those. They're relatively straightforward, but they do require a little bit of kind of looking at the data and figuring out what the best approach would be. The way that you perform these non-parametric tests, again, pretty straightforward. In our studio, there's a couple of functions, and you basically put the data in, and it produces the result. The consequences of non-parametric testing, I already mentioned this, they are robust. So if you have wonky data, if you have outliers, if you have high skewness, strange variation in the data, then they will provide you still with a valid result. They're less powerful because you strip away information and replace the raw numeric value with its rank. And then the strategy that I usually take with analyses, if I can't do some minor transformation to the data and get the parametric, the more powerful parametric test to work, then I default to the non-parametric test, because I know it will be less likely to give me a false positive result. And then here's that hierarchy I told you about. When we're looking at a continuous variable and we're interested in its central tendency, its average, whether that be its mean or its median, as a function of the number of groups that you're comparing and whether or not you meet the assumptions or do not. So if you have and this should not just say normal, it should say assumptions are met, assumptions not met, or you have too small of an n. And then whether or not you have independent samples, or are you doing repeated measures, or is there some kind of matching between your samples? And so you can see all of the different possibilities. Let's suppose now that you have a categorical outcome. So a patient responds or doesn't. If they respond, maybe there's an ordinal classification for response, like we have in the criteria in cancer studies, where you go anywhere from a treatment failure to stable disease, partial response, complete response. So it's now, if we think about levels of measurement, we're now on that lower end for nominal and ordinal variables. The different kinds of tests that you'll hear a lot about when your outcome is categorical. You'll hear a lot of chi-square tests being applied, and there are, unfortunately, many different types of chi-square tests. You'll hear Fisher's exact test, logistic regression. Those are probably the most common ones. So if you have a single group where you're measuring a categorical outcome, you'll hear about the chi-square goodness of fit test. You might also hear about the binomial test or the multinomial test. If you're comparing groups, either 2 groups, 3 groups, 5 groups, 10 groups, you'll hear the chi-square test of independence. And that's different from the chi-square goodness of fit test, but they're both chi-square statistics. This always trips people up in like stats classes. Which chi-square test is it? Fisher's exact is a kind of a non-parametric version of the non-parametric equivalent for categorical independent variables and a categorical dependent variable. And then logistic regression can be done with a single categorical variable for X and a single categorical variable for Y. It's nice because it produces things like odds ratios for us very easily. The assumptions around statistical methods for categorical outcomes really revolve around the sample size, only because yes-no data, you don't have a distribution for that, right? It's either a certain fraction or yeses, a certain fraction or nos. So the idea is we need to have enough yeses and nos in the data to get information about what's happening. If you have a very rare event, then you're going to have an enormous sample size to get enough yeses in your data set. So again, it's kind of tied to how big is the sample size and what is the rate of each of the possible outcomes in the sample. It has to be big enough for it to be informative. These can all be done in RStudio. And then I'm going to do some examples for that in just a moment and show you the rules of thumb, both for the t-test and for those chi-square tests. But before we go too far, I want to review what we talked about last week for hypothesis testing, where the premise is that subjects who are treated differently tend to differ more in their outcomes than subjects who are treated the same. And you see that nicely here in what's called a box plot. Box plot represents along the x-axis here the categorical independent variable, which in this case happens to be which treatment was received. And along the y-axis, the continuous response. And the box itself, so the response is on the y-axis. The box itself, between these 2 points, we have 50% of the subject's responses. So this is like the inner half of the data. And then the whiskers go out. You'll have to make sure, it depends on the statistical software that produces it, but they tend to go out a certain distance, either a function of a formula or all the way down to and up to the extreme values, the minimum and maximum in the data set. This one I know is not going out to min and max because look at this guy right here. There's a dot here. So there must be a formula or something that, this is produced in R, that is deciding how far out these go. And any observation that's beyond that calculation is flagged as an outlier. So for this one, we have one outlying observation indicated by that circle there. This distance right here is what's called the interquartile range. Has anyone ever heard of the interquartile range? So everyone knows what the range is. The range is the distance between the minimum and maximum value. For this one, we can see the range. It's between this minimum value and that maximum value. So that has a number associated with it. The interquartile range is just that it's a range, but it's the range between the 25th percentile and the 75th percentile. So that the inner part, so it's more informative in that it's robust to things like this, because that is actually inflating an estimate of the range of the data because it's an unusually large observation, whereas this kind of describes the inner 50%. And then another feature of the box plot is this solid line here, which is sometimes the mean, sometimes the median, but here it's actually indicating the mean. And so usually when we have two groups or more groups and we're measuring a continuous outcome, we're really after, are those mean responses, the average response is different. That's why a box plot is very useful for visualizing data in that circumstance. So you can see here, subjects who received this treatment, their responses are lower in general than subjects who received placebo. And that's the premise behind hypothesis testing. We set up statistics in a way to be able to detect this variation, this particular type of variation in groups. What if we have a categorical outcome? Categorical outcomes, you can't use box plots, right? Because they're yeses and nos. There is no distribution of responses. There are only zeros and ones. So it would look kind of weird. In fact, I could produce a box plot for you, but it would be all there at the bottom, right? Because it would be nothing but ones. With a categorical outcome, it's better to see something like this, where you see the categorical X and the categorical Y simultaneously in one figure. So this one happens to have the treatment on the Y-axis, and then you see the categorical response, whether or not they improved and by what degree did they improve on the X-axis. And it allows you to see not only for the entire study sample what fraction were treated with the treatment versus placebo, and it looks like it's about 50-50 in terms of like the height of these boxes, maybe a few more in placebo. It might just be my eyes. And then also within placebo and within treatment, what fraction of those subjects responded in what way. So no improvement is obviously higher. There's a higher fraction of no improvement in placebo than in treatment. Some is about the same, and then you see a big difference here in the terms of market improvement. So there's much more positive outcomes in the treatment group than there are in placebo. I've been using some terminology I probably better very quickly define before we move forward. Independent variable is the variable that's being manipulated by the researcher in an experiment, or it is the hypothesized cause of variation in the dependent variable. But you see this nomenclature, it actually varies from field to field. You might hear an independent variable called an explanatory variable, a predictor variable, an exposure, or a risk factor. Those are usually hypothesized explanations for outcomes that you see. And the dependent variable is the outcome. That's the value that we expect to change as a function of changes in the independent variable. So you hear that sometimes called the outcome or the response. Let's go back to the LDL cholesterol. I think we talked about this last time in the context of a single community. Now let's take it beyond that. Let's look at two groups. Maybe there's two communities. Maybe there's two drugs applied to a single community, whatever. In this case, I've got two competing drugs, A and B, that are used to treat individuals with high cholesterol. And we're going to see whether or not there's any difference in the way patients respond to these two drugs. And the response is a function of their LDL cholesterol levels. So we actually have hypotheses. If you'll recall, we have a null hypothesis, which is actually the thing that we think is not true, generally speaking. We think that there is a difference in the way patients will respond to these two drugs, but we want to invalidate or nullify the hypothesis that states that they're equivalent. So again, alternative hypothesis is generally a statement of effect or difference. The null is generally a statement of no effect or no difference, and it's in hypothesis testing the one we wish to reject or invalidate. The null hypothesis, in step one of hypothesis testing, we actually proceed as though the null is producing the data that we're observing. We assume that it's true in order to figure out how different the observed data is from what we would expect if the null actually were true. So the way we do this is through a test statistic. The idea is that if the null hypothesis is actually true, if there is no difference in the way patients respond to drug A and drug B, then the data should yield similar average LDL cholesterol levels in the two groups. And I note should, because there's always a chance, remember last week, always a chance that you could get a sample that's not reflective of the truth simply because of this nuisance called sampling variability. So we have to quantify what that risk is. We quantify that in our study design by the type 1 error rate. So the type 1 error rate, when we communicate that, when we design our study to control that, what we're doing is we're minimizing the chances of a false positive finding below some threshold, usually 0.05. But again, think critically about the consequences of a false positive finding before defaulting automatically to 0.05. It might need to be 10%, it might need to be 1%, depending on the consequences. If the alternative hypothesis is true, theoretically, we should get two samples, one group of individuals treated with A, one group of individuals treated with B, whose responses differ. That should be reflected in the sample data. But again, sampling variability means that there is a risk of a type 2 error, which is the probability of a false negative finding. And we incorporate this into the design. We design the study in such a way that we minimize this and we maximize what's called power. Power is just the inverse of the type 2 error. It's our chances of a true negative finding, which is often what we are looking for. True positive finding, sorry. So I like pictures rather than just talking about this. So there's two potential realities. The reality on the right is if there really is no difference in the way patients respond to drug A and drug B. And how do I know that that's that reality? The x-axis reflects the difference in average LDL cholesterol for two different groups, one group treated by A, one group treated by B. If there's no difference in the way patients are responding, then the difference is zero, right? So notice that the average, that this distribution is centered around zero. This distribution represents the kinds of samples that could be produced if the null is true, which is why it's not just a line at zero. Because even if the truth is zero, because of sampling variability, we could get something that's a little bit less than zero or a little bit higher than zero. We could also, unfortunately, if sampling variability has an impact, a big impact, we could even get something that's way out here in a tail, something that's relatively large and in disagreement with the null hypothesis, again, because of sampling variability. So this distribution represents the types of differences that could be produced by this experiment as a function of sampling variability. Most likely it'll be zero or somewhere really close to zero, but it's possible it could be out here in the tails. This other reality, which is dashed, it looks just like the null, only it's shifted. It's actually shifted to around -10. So there could be this other potential alternative reality. It's kind of funny phrase for this situation, but it's an alternative hypothesis for what we're seeing produced by the data. So let's suppose that the truth is that actually there is a difference and it's a 10-unit difference. One of these is producing LDL cholesterol levels that are 10 units lower than the other, which means that this distribution's shifted over. We're more likely to get means from these two groups that are 10 units apart, but because of sampling variability, they could be, somewhere in this region. The unfortunate thing is you see overlap in these two distributions, right? So if I get a really strong result, like I treat two groups, one with A, one with B, and their LDL cholesterol levels are 141 and 140. Depending on what things look like, that's only like 1 unit up. It's not very far from zero on this picture. It's pretty clear that I should be picking the null. So I'm not rejecting the null in the situation, right? Does anybody here want to pick the alternative for that, given this picture? So in this case, I fail to reject the null, right? Because this is pretty much in agreement with that reality. I could also get a really strong effect in the other direction. Suppose I treat two groups. One group's LDL cholesterol is 125, and the other one ends up with an LDL cholesterol average of 140. Does anybody here want to select the null as producing that result? It's pretty clear that the alternative hypothesis here is more likely given the observations. So in this case, I reject the null hypothesis in favor of something else, right? In favor of the alternative. Where hypothesis testing really helps is when you get this in this gray area. What if I treated two groups whose outcomes indicated just a 5-point difference in LDL cholesterol? The question here is that big enough? It turns out if it's right here in the middle, it's almost like a coin flip, right? It's a coin flip between the null and the alternative. This is why we design studies beforehand to control type 1 error, because before I see this data, I'm going to pick how strong, how different these two need to be before I say that it's the alternative rather than the null. And if it's big enough, then I know that my predefined threshold has been met, as opposed to letting the data tell me. Because at this point, if we didn't select that kind of threshold, that cutoff point at which the alternative becomes more likely, in our opinion, then we're kind of stuck here, right? So how do we do that? How do we set that threshold? Well, we do it in a way that, given our sample size and some assumptions about what we think the behavior of LDL cholesterol is in this population, we set that cutoff value to minimize the risk of a false positive finding below 5%, for instance, below 10%, below 1%. And then we compare our observed value to that, what's called a critical value. The critical value is the threshold. And we do that using a test statistic. And again, this is a reiteration of what we talked about last time, but I wanted to introduce to you the chi-square, because the chi-square is appropriate for categorical data. And the t, which we saw last time, is appropriate for continuous. In the t, we're hypothesizing about means. So remember, the test statistic quantifies the evidence of a real treatment effect in a standardized format. It comes in the form of a ratio where the numerator is the signal and the denominator is a measure of the sampling variability or noise. So in the t, we're hypothesizing about means. So we hypothesize that there's no difference. This is a 0. And this is whatever the difference was. So this is the deviation between the observed data and the hypothesized data, or the hypothesized reality. And the bottom is the standard error of the mean, which is a function of both the sample size and the standard deviation of LDL cholesterol. So this is a measure of sampling variability or noise. If the signal is large relative to the noise, then we know that it's a real, quote unquote, real signal, as opposed to just sampling variability producing the result. For the chi-square statistic, look at the structure is the same. Instead of having a sample mean and a population mean, we have an observed count and an expected count. And we'll see an example of this in a moment. But the difference between the observed data and the hypothesized data is the signal, and we standardize it by what's essentially noise. It's like an event rate, if you will. And we'll see that in a moment. But this one operates in the same way. It's a signal to noise ratio. So if it's big enough, then we know that there's evidence of a signal. If it's big enough, there's evidence of a signal. So back to our LDL cholesterol example, let's actually calculate the T, which would be appropriate in this case because I have a 2-sample test of continuous data, so I'm comparing means. All I'm showing you now is the null hypothesis, because remember, a step 1 in a hypothesis test is assume the null is true. We just totally remove the alternative. Assume the null is true. The T test statistic for each of these combinations of means, so remember over here it was a 15-point difference. The T, when I calculate it, if I take the difference in the means and I divide by a measure of the sampling variability, I get a T of minus 7.5. Can someone in English interpret what this means for me? Not saying reject or fail to reject. What does this tell me about how far away the observed effect was from the hypothesized effect? This distribution is telling me the kinds of effects that are likely to be produced by an experiment if the null is true. But I produced an effect 7.5 standard deviations below what we would expect to observe if the null was true. Do you need a p-value to interpret this? No. Everyone understands that 7.5 standard deviations is a highly unusual value. So this tells me I'm probably going to reject the null. For this one, visually we see it, but you can see now what the T means. The T for that 1 unit difference, 140 and 141, so there's 1 unit difference between the two means. The T computed from that is 0.5. So this one is half of a standard deviation above what we would expect. It's a likely value. If the null could have produced that very easily. The null probably didn't produce this one. The chance, but the chance is like 0, right? Almost 0. The question here is, what about this one? This one is actually 2.5 standard deviations below what we would expect. It turns out if we set the threshold to minimize the risk of a false positive finding to 5% or lower, this is above that. Does anyone know what the critical value, the T value is approximately, or even the Z value approximately for 5% alpha? It's around 2, give or take. T is a function of sample size, Z is not. So it's around 2. This is 2.5. So the usual cutoff is around 2, and this is 2.5 standard deviations below. So this is a less than a 5% chance of a false positive finding, given this particular study. Unless you wanted to be at 1% or 0.5%, then you're probably going to reject the null hypothesis and attribute this effect to an alternative hypothesis. So reject the null. And again, why? It's because of that predefined criteria, the predefined threshold. So in this case, the question was, is there a difference in the way patients respond to these two treatments? We rejected the null and state that there is a difference because this observed effect is bigger than what we said before we saw the data the effect needed to be for us to be confident that it was a real difference. Now let's ask ourselves a second question, because this is how we interpret the p-value. Again, how do we interpret p-values in the context of a design study? If no relationship actually exists, in other words, if that is actually the reality that produced this finding, if no relationship actually exists between the type of treatment administered and LDL cholesterol levels, what are the chances that this sample inaccurately depicted a difference? And that's the p-value. So, and the p-value for this, if I do the math, it's 1%. And so you have to ask yourself, am I comfortable with that? I'm comfortable with that, right? There's a 1% chance that this is a false positive finding. Questions? Okay, so back to inferences concerning two groups. Let's just take a look at the two most commonly applied methods, the t-test and the chi-square test. It's pretty clear. One's for continuous outcome data, assuming that outcome data follows you can verify the assumptions of normality and equal variances. Chi-square test is appropriate for categorical outcome data, either ordinal or nominal. In the t-test, you're comparing the average outcome, the average response between two groups. In the chi-square test, you're comparing the frequencies of responses across different categories. And you're doing that in terms, you can do it in terms of what's a proportion or a percentage, or you can think of it also as in terms of risks, depending on the kind of study. Some examples of the questions are average LDL cholesterol levels for patients treated with A the same as those treated with B, or are they different? For the chi-square test, are the percentages of people developing a disease the same in an exposed group and an unexposed group? So that's getting at risk. You see that a lot in public health or more observational studies. Here's an example of the categorical analysis. Looking at early cardiovascular death. This is an observational study where it's done on surveillance data. Has everyone here heard of the SEER registry, S-E-E-R? Surveillance, Epidemiology, and End Results Registry. So it's just collecting data from individuals over a prolonged period of time. It's not a randomized controlled trial or anything, and they're just looking at, actually they're looking at a lot of different things, but it allows them to collect a large amount of data on lifestyle behaviors, exposures, and other risk factors, and then try to link them or hypothesize about their links to patient disease and survival. So in this case, the study was done using SEER data on individuals who received a diagnosis of cancer between 1998 and 2008. So that formed the cohort of individuals that they were interested in, the population of individuals they were interested in. And they recorded the number of individuals who experienced cardiovascular death. The independent variable in this case had to do with whether or not the individual who had a diagnosis of cancer received surgery. So that's the predictor, if you will, the exposure. So they either had surgery or they did not. The dependent variable, and notice it's surgery to the primary site. And then the dependent variable, the outcome was cardiovascular death within 1 month after their diagnosis of cancer. So it was also yes, no. So we have an independent variable that's categorical and an outcome or dependent variable that's categorical. So chi-square test is appropriate here as long as our sample size and event rate is high enough. So the hypotheses in this case, before I showed you that we hypothesized about means using that kind of script M, which is just the Greek letter mu. Here we can hypothesize it in many ways, and you can even just write out the mean. It doesn't matter. It's just notation. But in your stats classes, you usually have specific symbols that represent different features of a population. Here we're hypothesizing that the rate of cardiovascular death for individuals who receive surgery versus those who did not receive surgery is different or the same. So we think it's different. That's the scientific or alternative hypothesis. But we have to assume that it's the same and then perform the chi-square test to see if the evidence is strongly enough in favor of the alternative for us to reject the null. So in the results of this study, this published study, they say using a chi-square test, we found that cardiovascular death was significantly more common in patients who underwent surgery than in those who did not. Notice they produced the p-value for that assertion, which is very small. The risk of this being a false positive finding, according to them, is less than 0.1%. But they also give you the effect size, which is also important, right? You can't just interpret the p-value by itself. You see the data and you see the difference in the rates. 12.3% in those who received surgery versus 5.5% in those who did not. What is the problem, though? It is true that it was significantly more common in patients who underwent surgery based on this data. Are they saying that surgery is causing an increased risk of cardiovascular death? They very clearly don't say that here, right? And we should not interpret it that way. Why? This is not a causal study, right? This is observational. The p-value, as well as these statistics, 12.3 and 5.5%, are not functions of sampling variability and treatment alone. What other things could they be functions of? What other things could be here causing differences in patient outcomes, aside from sampling variability and treatment? Severity of the cancer, type of cancer, primary site location, comorbidities, age, where the surgery was or was not performed, kind of thing, right? So again, p-values provide an estimate of the role of sampling error in the findings of a well-controlled, well-conducted experiment. This generated a hypothesis for us. It did not confirm one.
I have a question. How do they choose that p-value less than 0.001, less than 0.05? How to determine like the p-value?
What the p-value needs to be?
Yeah.
They do that in a study design. You actually link the sample size to the clinically meaningful difference that you want to be able to detect. And then they think, well, to be frank, most people just pick 0.05, right? That's the threshold. And I understand why. It's because it's really hard to change the way we do things. But the consequence of selecting 0.05 is that if you don't put thought into what the rate really needs to be, then you might be missing a meaningful effect or saying something is meaningful when it actually isn't. So I'm hoping that if you do a study, your selection of an alpha level of 0.05 is grounded in the consequences of a false positive finding. And does that need to be 5% or should it be stronger? Should it be 1%? Or can it be relaxed to 10%? And I think it really, if you think about, and this p-value, the observed p-value, by the way, is calculated from the data, right? So that p-value came from the fact that they saw 12.3 and 5.5 in, my goodness, 200,000 patients. So that's where that p-value came from. By the way, it's not very difficult to get a small p-value when you have 200,000 observations. But think about it in the context of drug development. So the way the FDA has set up the drug development process is that we start small and we generate hypotheses, and then we have this spectrum of study designs to confirm, right? And confirm again before we start treating people with that drug. Because it needs to be both safe and effective, and the risk-benefit needs to be adequate. Early on, let's suppose we're treating, and I think I gave this example last time, let's say we're treating migraines, which have treatments. There have actually been some really good treatments recently that have been developed. The consequence of missing a promising migraine drug, so that's a false negative. The consequence of a false negative finding in a migraine study, now I don't suffer from migraines, so maybe I'm incorrect, right? That is less damaging to the patient population than a false negative finding for a condition that's currently got no treatment that also has poor survival. For instance, I think I gave pancreatic cancer last time. So there's a consequence for missing something that's there, and there's a consequence for saying something's there when it's not. And so you have to think about it in terms of benefit and risk, honestly. The benefit of making a correct decision, the benefit or the risk of making an incorrect decision, whether it be true positive, false positive, true negative, false negative. And that should be set where it needs to be set. Typically early on, we relax it. Power is more important. Power and type 1 error are very important right before we get to the population, because we want it to be powerful and we want to confirm that this is a true positive finding. Early on, we can kind of relax those things because we're generating hypotheses. Now, we can't just totally relax them, but they might not need to be 5%. So I think just thinking about the consequences will be helpful and discussing them as a group. So again, this particular test should be considered hypothesis generating, as there are many other potential sources of variability contained in the p-value other than sampling variability. And all those things that we just discussed are called confounders. They could be the thing, they could be unfortunately associated with whether or not a physician decides to actually intervene surgically on a patient. Maybe the patient's already really sick, and so they decide not to intervene with surgery. Or maybe their cancer is at a more advanced stage, so they decide to try to do surgery because that's the only thing that might work. I don't know. I don't know what goes into the decision-making with regards whether or not to give someone a recommendation of surgery or not. But those could be the things driving the effect that you see here, as opposed to the surgery itself. Another example for inferences on more than two groups. So we went through the t-test, the chi-square test for comparing two groups. What if we have more than two groups? Here's an example in smoking cessation where the outcome is considered continuous. It's kind of a count outcome more than anything, but it is considered continuous. And now we have 3 treatment groups that we're comparing: literature, behavioral therapy, pharmaceutical therapy. And the goal is to get smokers to quit and to stay quit. And then, again, this is a contrived example. Rather than looking at quit rate, we're going to look at the reduction in cigarettes. Hopefully there's some kind of change in their behavior after 6 months of therapy. So this hypothesis, again, the alternative hypothesis, the scientific hypothesis, is that we think that one of these, at least one of these, might be better at getting people to quit or reduce their smoking than others. That's the alternative. The null is that they're all equivalent. They might all be great, they might all be poor, but they're all the same. There's not one that we would recommend over the other. The approach, and I've seen this approach taken, is that sometimes you just do a t-test comparing each intervention to the control. And the control in this case is the literature group. Does anyone, we've already talked about it, but does anyone know the problem with doing a bunch of t-tests here? So you do 3 t-tests, right? First group to second, first group to third, second to third. What's the problem with doing 3 t-tests? The type 1 error, right? So the more tests, the more you look for something, the more likely you are to find it, even if it's not real. You could still do a t-test, multiple t-tests, but you would have to do adjustments primarily to your sample size. You'd have to increase your sample size and pull in, if you will, on your alpha level, your type 1 error rate for your individual tests in order to make this experiment valid and to keep that type 1 error rate contained. But that's inefficient. So rather than do that, a person named Fisher developed what's called analysis of variance long time ago. And it provided a way of basically finding differences in means between many groups in a much more efficient way, because it controls the type 1 error without making huge adjustments to the sample size. So how does analysis of variance work? It's really strange whenever you think about the term analysis of variance, because we're comparing means. So why is it an analysis of variances? And it's actually pretty straightforward. The idea here is that, just like with the T statistic, we have a signal on the top, which is like patients who are treated differently respond differently. That's the signal. And then you have the noise on the bottom. Patients who are treated similarly respond more similarly than patients treated differently. And it's the same concept with the box plot here. So what it's doing, ANOVA, is actually comparing the average across groups. But it's doing it in a way that it's actually doing it as a function of variances, as opposed to, I'm going to skip those slides because I want to show you the picture. So it's doing it in a way that the calculation is a function of variances as opposed to means themselves. And the reason why we take this approach is because this is the approach that controls the type 1 error rate, makes it much more efficient. So let's suppose I have 3 different studies. Study A, I should have called this A, study B, study C, and in each of these 3 studies, we're comparing 3 different treatments, 1, 2, and 3. There's an obvious difference in the results of each of these 3 studies. Which of these do you think produced a statistically significant treatment effect? Number 1. It's pretty clear, right? So number 1, you can see that the means, in particular of this one, are different. Number 2, they're kind of different, but there's a lot of overlap. And number 3, there's really no difference. So the idea here is we take and measure the variation in patient outcomes, but we're also measuring the conditions that produce the patient outcomes, like what was their treatment, maybe some other features that we want to adjust for. And then we try to partition the variation into, in the simplest case, 2 different sources. So we have some variation that's attributed to what what treatment the patient actually received. And then we have the other variation that we just attribute to error. And then we take those sources of variation and we make a ratio out of them. And then just like with the t and the chi-square, if the ratio is large, there's a lot more variation among outcomes for patients that were treated differently than there are for patients who were treated the same. And we do that using a ratio, and that ratio is called the F test statistic. So the idea is if the between treatment variation is a lot bigger than the within treatment variation, that suggests there are some different effects among the treatments. So let's take a look at this. When I say within treatment variation, you can visualize within treatment variation. There's the within treatment variation for treatment 3. There's the within treatment variation for treatment 2, and the within treatment variation for treatment 1. And that variation is pretty consistent across all 3 groups, right? So we've achieved homoscedasticity or equal variances between groups. The other question is, why does it say new share? The other question is, well, what do we mean by a kind of across groups? That has to do with the variation that you see in this direction, not within the box plot, but across all the box plots. So how do the box plots themselves vary? And so the numerator variation has to do with quantifying that variation, and the denominator is like an average of these 3. That's why the denominator being an average of those 3, that's why it's important for them to be approximately the same. Otherwise, you can get an invalid estimate of the within group variation. And there's my nice little animation showing you that, yeah, indeed, that one is bigger than the other. Is it big enough for it to be flagged as statistically significant? Well, that depends on the study design and how you set those parameters. You can see here that in scenario 2, we have a problem with the within group variation being the same. It's kind of all over the place. This one's very tight with a couple of outliers. That could actually throw this analysis off. So even if the pattern is there in terms of the means being different, you're likely to miss it because the variation in the data doesn't meet the assumptions of the method, and also because there's quite a bit of noise here. And this is true here as well, that there's a lot of noise in 3, but in general, the means are the same. So again, the F test statistic, I'm not going to give you the formula. I'm just going to give you what it's really representing. On the numerator, you have variation between sample means. The denominator, you have the variation within the groups. And if we take a look at what values F can take on, so we know that t equals 0 indicates really no signal. What indicates no signal for F? The answer is not 0. This is a ratio, right? So when are the numerator and the denominator the same? What is the value of F? 1. So a value of the F statistic that's relatively close to 1 would indicate no signal, no treatment effect. Something bigger than 1 would indicate it would be evidence of a treatment effect. And why do I say bigger than 1? It's because we know variances are always 0 or positive. So F will never be negative. It will only ever be 0 or positive. So I've already answered the questions here. You cannot get an F that's negative, and the values of F close to 1 would be ones that would be in support of the null. When you do analysis of variance, you get an ANOVA table that's really cool. It actually gives you the variances that you're comparing. So what you see in a ANOVA table, the concept here is that we take the variation in the outcome and we try to attribute certain amounts of that variation to different sources. So here we have a treatment. We'll call that treatment factor X. Maybe this is whether or not they received the treatment, for instance. And then we have, in this case, this output is produced by R. We have a row called residuals. That just is error. So it's either attributed to the treatment or it's attributed to error. You could get a much more complex design and apply a much more complex ANOVA model where you have many different sources of variation. Each source of variation has what's called a degree of freedom associated with it. I'm not going to talk too much about that. Just know it has to do with kind of how many calculations were required to get to that. So like for instance, this one had three levels, so there's 2 degrees of freedom. And then the sum of square, again, don't worry about that. It's the mean square that you want to take a look at. The mean square, and I've already alluded to this a couple of times, in statistics we like to call the same thing by different names depending on what the context is. So for instance, ANOVA is just linear regression. Did you all know that? If you do ANOVA, you are doing linear regression. It's just a linear regression with a categorical X. That's all it is. A mean square is just a variance. So the term mean square is what a variance is. A variance is like an average deviation squared divided by the sample size. So the mean square is the variance between groups. This mean square is the variance within groups, because this, remember, the within groups is the measure of the error variation. And where this variance comes from, they don't even really need to show you the sum of squares in this table, but they do it so you can see the components that make that up. So when we think about an average, a mean, you add up all the values and you divide by the sample size. Well, this is the sum of all of those squared values that make up the variance, and that's what you divide by. So if I took 1378 and divided by 2, I should get 689. So that's primarily the reason why you would see these two things given to you in a table. But this is the variance between groups. This is the variance within groups. And if we take a look, we can see that the variance between groups is much, much larger than the variance within groups. And in fact, I can do a ratio of those two, 689 divided by 30.4, and get a 22.64. So how do I interpret the F? For the T, if the T is negative 7.5, we already said that that means that the observed effect is 7.5 standard deviations below the effect that we would expect to get if the null hypothesis was true. The 22.64, this is a ratio, right? So this, what we're saying is the variation between groups is 22.5 times as large as the variation within groups. Does anybody need a p-value for that? No, but you report it anyway, right? It's really small. That's scientific notation, which just says take that decimal point and move it 8 digits to the left and put a bunch of zeros. So it's basically 0. So the interpretation is the chance that this is a false positive finding is essentially 0. This is a very large effect that we're seeing here. So how does this apply back to our hypotheses? Does it really tell us what we're after? Well, it does tell us that we should reject the null. That the fact that the means are the same, if we have equal variances between groups, should indicate that the mean square between groups is equivalent to or really close to the mean square within groups if there's no treatment effect. But this is saying they're not, it's actually much larger, reject the null. And the interpretation here is not that any one particular, it doesn't tell us which of these groups is different. It just tells us that there is some difference among these averages. We have to go and do a little bit more work to figure out where the averages are different. And how do we do that? We do that with what's called a post hoc comparison. A post hoc comparison just means you're doing it after you did the test that preserves the type 1 error rate. So when I know there's a difference, then I can go looking for it. And there's not as many severe consequences. And there are many, many different ways to do that. There's something called Tukey's approach, which I'm showing you here. There's also a Fisher's approach. There's other approaches that involve Bonferroni, and you'd have to take a course in experimental design to differentiate between them all. But just for instance, Tukey's. We found a statistically significant difference somewhere. Where is the difference? I'm using Tukey's post hoc comparison, which is nice because it does all pairwise comparisons. So it's comparing literature to behavior, literature to pharmaceutical therapy, and then behavior to pharmaceutical therapy. So the A and B, C and A, and C and B here, this is our output, indicate what the treatment comparison is, and it gives me an estimate of the difference. So if I took the average of B minus the average of A, so the average response for individuals receiving, behavioral therapy, and subtract from that the average for those receiving the control, the literature, I'm seeing a 6-unit difference. So this is 6 cigarettes higher, for instance, in terms of reduction than the other one. This is kind of a complicated interpretation, but just know that this is the difference between these two means. A bigger difference exists between A and C, so the behavior and the pharmaceutical therapy. The pharmaceutical therapy actually appears to be more effective. And then when we compare behavioral B and pharmaceutical therapy C, there's a 5-unit difference. The difference alone doesn't tell us a lot. We have to really look at the confidence interval on that difference, because if these differences are, these means are the same, then the confidence interval will contain what value? If two means are the same, when I subtract one from the other, what do I get? 0. So let's look at the confidence interval, which essentially is telling me that's the estimate of what the value is likely to be. As small as 2.5, as high as 10.8. That's the difference. A 0 contained in there. There's no 0, which tells me that there is statistical evidence that the average for A is different from the average for B, because 0 is not in the interval. 7 to 15, 0 is not in that interval. 0.8 to 9.27, it's getting close, but it's still above 0. And that's reflected in the p-values, right? This is kind of close to 0, so the risk of it being a false positive finding is about 1%. These others have p-values that are very strong, less than 0. So again, in order to figure out where the differences are, and in this case, they're all different to some degree. Some differences are stronger than others. You have to do a post hoc comparison. So in this case, I'm just giving you an example of what this write-up might be. There's much more that needs to be described in terms of what the actual effects were, how much reduction or how much benefit you saw among the 2 experimental interventions, but it's just showing you some things that you could add. Okay, so finally, inferences on means. It concerns a continuous response. You can do one group test or a 2-group test using a T, again, assuming independent groups. If you have more than 2 groups, do ANOVA. Remember that the 2-group and the more than 2-group tests are really just tests of association. Anytime you have 2 variables, an independent variable and a dependent variable, and you're doing a statistical test, it's a test of association, regardless of whether it's a T, an F, a chi-square, or correlation coefficient. Make sure, though, that you check the assumptions of the method. If your sample size is too small to verify normality or equal variances, err on the side of caution and do the non-parametric version. For the t-test, it's the Mann-Whitney, sometimes you hear it called the Wilcoxon or the Mann-Whitney-Wilcoxon test. And for the ANOVA, it's the Kruskal-Wallis test. And those are in most statistical software packages. And again, the 2 assumptions, normality and equal group variances, are given there. I already mentioned that we're kind of keeping it simple today. You can't even probably read this. Just know that all the tests that I've done today are some variation of a regression model. And depending on how many sources of variation you have in your experiment that you either controlled for or you measured, your model could become pretty complex. And so depending again on what your study design is, you can see there are almost an infinite number of ANOVA models that can be applied. And but the model is tied back directly to the design. The simplest ANOVA model is the 2-sample T, and they're all regression. They're just trying to attribute variation in an outcome to a factor of interest. Now let's look at inferences on proportions again, but now we have more than two groups. Here we have, I shouldn't say more than two groups. We do have more than two groups, but it's actually on the dependent variable as opposed to just a yes-no response. Now we have an ordinal response. So for cancer studies, very often when we're looking at patient response, we do it based on imaging. So we measure the tumor or the lesion using some kind of imaging technology prior to treatment, and then we have repeated measurements over time after treatment has happened or while treatment's happening to see how the tumor or the lesion is changing. Hopefully it's shrinking or going away, but it's possible that it's staying the same size or it's even growing. And so the way we classify that response is a pretty complicated rubric, but in the end, a patient is assigned one of these 4 responses. A complete response means that's kind of the best response you can achieve. Usually it means that there's no visible disease remaining at a certain period of time and it's sustained for a certain period of time. Partial response is not quite as stringent as a complete response, but it's still a good outcome for the patient. Stable disease could also potentially be a good outcome depending on what the disease is. It basically means that the disease didn't change in a very discernible way. And a failure means that the patient usually progressed. So this is a categorical response, and also it's ordinal because this is the highest level and this is the lowest level. And the question that we have here for this randomized controlled trial where we're looking at 2 competing therapies, A and B, is what is the pattern of patient response between these 2? And so we have a categorical predictor and a categorical outcome. This is a chi-square test of independence. All we're really looking at is whether or not patterns of response or the way a patient responds is associated with the treatment they received. The assumptions for this, again, we're getting this data in the form of a contingency table. We have 300 subjects, 100 received A, 200 received B, and we have the count of subjects of these 100 across all of the different outcomes achieved, and then the count of this 200 across all the outcomes achieved, and then the total on this last row is just the sum, the total number of complete responders, partial responders, stable, and failure. And then the percentages you see in here have to do with the percentage of those who were treated with treatment A who had a failure, who had treatment failure. 32% is the percentage of complete responders among those who received treatment A, and so forth and so on. So that's a row percent. The assumptions here, again, really have nothing to do with normality or equal variances, only that we have an event rate high enough that all of these cells have enough subjects placed in them at the end of the study. So the way that we ensure that the event rate or that the cells here have enough subjects in them is that we have to target a sample size big enough to correspond with an event rate that will put more than 5 subjects in each of these cells. If we underestimated the event rate here, let's say it was only 1%, and we ended up with 1 subject in this cell, we probably shouldn't do the chi-square test. And if we don't have frequencies big enough, the Fisher's exact test is what you would apply instead. So what is actually being hypothesized here? The researcher is hypothesizing that response is not independent of treatment, and that is the alternative. In other words, that treatment is associated with how a patient responds, versus the null, and that there's no association. It's independent of treatment. A patient's going to respond the same whether they receive A or B. And the way that that looks is, what we're doing is we're taking a look at the table and we're trying to discern whether or not it appears that this type of sample that we see here, could it have come from a population where the rates of response occur with the same frequency within each treatment. So in other words, the question is 32% different than 27.5%? Is 43% different than 32.5%? Is 16% different than 32%? Is 9% different than 8%? Is the distribution of complete, partial, stable failure similar enough between A and B to say that these are producing the same response patterns? To do this, you do a chi-square test. And again, if you remember the chi-square test, I'd have to go back several slides, but the formula was an observed count, which are these numbers, 32, 55, 43, 65. And from the observed count, you subtract out an expected count. And the expected count comes from that null hypothesis where we assume that there's really no difference in the response rates. So there's a little bit of a calculation to get that expected count. Just know that it basically, it's almost like averages out these two. And whatever the average is, that's the expected value for the fraction of complete responders who receive A and B. And then if we deviate too far from that expected count, which would reflect equivalent patterns in these two treatment groups, then when we sum up those deviations across each of these cells, this chi-square statistic becomes very big. And so the chi-square here is 7.815. Its interpretation is not quite as straightforward because it's a function not of standard deviations. It's a ratio like an F. And so it's essentially the deviations are about 7.8. Hold on, how do I put this? The variation in these counts between groups is about 7.5 times higher than you would expect if there was no association between complete and partial, or excuse me, between A and B, and then the pattern of responses. So here, this is big. It produces a p-value of 0.029, so bigger than 1%, less than 5%. That's the observed risk of a type 1 error, but we decide because beforehand we thought 5% was the threshold for type 1 error, that treatment and response are associated. We reject the null that they're not associated. We don't want to just do that. We probably also want to visualize the data. So how could we do that? We could do it, if you remember again back at the very beginning of the slides, I had a single box and I had treatment A and treatment B and then the response patterns across there. That's one way of doing it. That's called a mosaic plot, by the way. I don't think I named that. You could also do it with just simple bar charts. So here we have treatment A and B. This is produced in Excel. I'm not sure why A is on the right and B is on the left. It's probably an oversight on my part. Along the y-axis is the percentage of patients who received that treatment who responded in that way. And then you see the 4 categories of response. And it's very clear very quickly that the red is much bigger and also that the green is much lower, and that's associated with A. So red, partial response is higher, stable disease is lower in A versus B. So that's kind of where we see the difference. And there are also post hoc methods for identifying which cells are statistically different that involve chi-square tests as well. But this functions much like an ANOVA, where you have multiple groups and you're trying to find which groups are actually different. And if here it appears that the partial response and stable disease are where the differences reside. You can do that. The overall chi-square test of association has a single p-value. But I could do a post hoc test and get p-values associated with each of these comparisons, 27.5 versus 32. That would be similar to the Tukey's test that we did with the ANOVA, because the ANOVA tells us there's a difference but doesn't tell us where it is. The chi-square test tells us there's a difference but doesn't tell us where it is. So it does require further post hoc tests, and those post hoc tests are chi-square tests. So you could do, and I didn't put them in here because I think more people are familiar with the post hoc tests for ANOVA than this, but you can do not Tukey's, but other chi-square tests to provide p-values. And yeah, generally speaking, when you do those comparisons, you would flag where the differences are here. Our final topic before we have to go, I'm going to touch on a unique kind of data. So again, today we've just been focusing on what kind of outcome do we have? Is it continuous or is it categorical? Well, what if it's both? And it's possible that it's both, right? If we think about a really common research question around survival of patients after diagnosis or after receiving treatment, there are two pieces of information in a patient's survival measurement. Number one, did they die or did they survive through a certain period of time? That's categorical. It's a yes-no response. But also number two, what else is associated with that measurement? How long? So we have both a nominal variable and a ratio variable simultaneously. And often, if we want to get at the real therapeutic power of an intervention, we need to know not only are they surviving or are they dying within a certain period of time, but how long? What is the pattern over time? Because it could be that if I'm just looking at a 5-year window and recording who's living and who's not living after a certain period of time, I could totally miss the effect of an intervention. Because maybe in intervention A, they all died within the first 3 months. Intervention B, they all ended up passing away within 5 years, but it was maybe around 4.5 years. So we have a prolonged survival. So when we have questions like, what is a person's chance of surviving 1 year post-diagnosis? We might also want to know what's the average time individuals with that diagnosis survive. And we cannot answer these questions with the t-test or the chi-square test. They're not designed in that way. But some brilliant statistician actually developed tools that will allow you to mine information simultaneously from the continuous survival time and the categorical event, yes or no, while managing the missing data that inherently comes with survival analysis. And when I say missing, I mean sometimes we have a study window of a year, and at the end of a year, patients are off study. They were still alive, thank goodness, because the intervention was maybe helping them, or they weren't, their disease was getting better. But if they pass away after that window, we don't see it. So that event is essentially missing. And that's a unique kind of missingness called censoring. And survival analysis handles it as well. So when we have inferences on time to event data, which again is both categorical and continuous, there are many different statistical tools that kind of fall under the term survival analysis. And it doesn't just have to be survival that's the meaningful outcome. You might be interested in, the development of a disease after an exposure, or the development of a disease in a cohort of individuals who have a particular genetic risk factor. You might be interested in how, the response pattern to treatment. You might be interested in the relapse of a disease. You might be interested in, I'm treating these patients, they have heart failure. I've done an intervention. They're discharged from the hospital. How long before they're rehospitalized because of their heart failure? That's also a survival analysis. Quitting smoking could be survival analysis, or restarting smoking could be survival analysis. So just know that the term survival doesn't always necessarily mean that the event is death. And it's a very powerful set of tools. If we're looking at time to event data in the context of survival, there's a couple of ways we can look at it. So I've shown you a picture here. You might have a healthy individual who has a disease and then at some point is diagnosed. Survival time in this context is defined as the time between diagnosis and or treatment and death, or some other event of interest. The diagnosis and treatment could also be an exposure, but survival time, just know it has to have some meaningful start and a measurable event. So 5-year survival simply describes the categorical aspect of survival analysis. It describes the percentage of patients alive 5 years after treatment begins, or 5 years after diagnosis, 5 years after exposure, and it's a measure of prognosis of a disease. Survival itself, just the term survival, has to do with a probability. It's the probability of remaining alive or event-free for a specific amount of time. And you often see that described with those Kaplan-Meier curves, which we'll show you in a moment. The unique feature, aside from the fact that this is both categorical and continuous data, has to do with missing data in the context of survival analysis. So missing data happens when subjects are either lost to follow-up, so maybe you need to observe them for 5 years, but you only, somewhere around 3 years, you lost contact, but you know that they were alive or event-free at that point of last contact. So we censor them at that date, and they don't contribute any information past 3.5 years. You might also have individuals who never have the event during the study timeline. So you never, if they had the event, you're not allowed to observe it. It happens after. And so those individuals are also censored in that we didn't see how long their survival time was. We just know that they survived up to the end of the study, and then we censor them at study termination. When we're able in a study to see everyone's event is measured, the study is said to be complete. I have yet to do a survival analysis where I didn't have some censoring though. And censoring looks like this. So for instance, let's say I'm doing a study that's a 12-month study. Individuals are receiving a treatment, and I'm measuring an event, disease relapse, for instance, or progression. But I'm only measuring them for 12 months once they've initiated therapy. So participant A receives therapy whenever they enter the study, and at study termination after 12 months of observation, they're still event-free. So their data, actually, their survival time would be 12 months, and they would be censored, indicating that they survived or remained event-free for at least 12 months, because I'm not able to actually record this. It's outside the study window. I don't know that the event at the STAR actually happened. Participant B, I was able to observe them have the event, and it was around 11.5 months. So I record their survival time of 11.5 months, and I also record in the binary outcome that they did indeed have the event. Participant C, let's say this is about 8 months, but then I lost them to follow up. So they could have had the event here, but I did not observe it because I wasn't actually able to keep in contact with this person. So they contribute, let's say, 8.5 months of survival time, and that at which point they're censored. And then participant D actually contributes the exact same information as participant A. I observed them for 12 months. They were event-free. They were censored at 12 months, even though this person never had this event that I was tracking, even after the study was over. So that's the information that you have in a data set when you do survival analysis. You have the time and whether or not they had the event. If they had the event, then you mark that. If they didn't have the event, or were not able to observe it, then they're marked as censored. So the different functions of survival time, the biggest one that's reported, well, I shouldn't say the biggest, probably the most common, is the Kaplan-Meier curve. I'm sure everyone's seen a Kaplan-Meier curve, and that's actually representing survival, where the survival function is a function that describes the probability that an individual in the at-risk population survives longer than some particular time t. And so you see something like this. On the right-hand side, this is a study where they're looking at transplant data. And on the x-axis is time. So time starts, the beginning of survival starts at 0, which is the transplant date, and they follow them out for 8 years. Along the y-axis is a probability. And notice it starts at 1 because at baseline, all of your study subjects were alive, right? So they're 100% were alive. So the chances of surviving in the study, 0 days is basically 1. But then you see as time passes, these lines are dropping, and they're dropping down to correspond to how many individuals. And this, I shouldn't say this is survival. This is melanoma-free survival. Melanoma-free survival. So with each subsequent drop, what you're seeing is a patient or a subject on this study experience that event. In other words, they were no longer melanoma-free as of that time point. So the faster this curve is dropping, the more quickly these events are happening in that particular cohort of patients. And so if the event is a bad event, curves that drop faster represent treatments that are underperforming. Curves that don't drop as quickly represent treatments that are better. So you can see here a comparison of whether the donor was living or cadaver. You also often see with these curves, these numbers at the bottom, which represent the number of subjects or patients or individuals that are represented in that line. They're currently at risk of having the event. So the living donor at baseline at 0, they're measuring 68,329 patients. By the time they get to 2 years, whatever the difference between 68 and 45,000 is, 20-something, 23,000. 23,000 either had the event or were censored. And so how do we know how many had the event? Well, we look to see how far did it drop in 2 years. So in 2 years, if I go up to the line and then I go over to the axis, it's 99.55% were still melanoma free. One really interesting thing about this figure is it doesn't drop down below 99%. So only ever 1%, right? 1% or fewer have this issue with melanoma after a transplant. That's why this is blown up the way it is. Often, though, you'll see the axis go from 1 all the way down to 0. Because in some studies, if it's complete, then the curves should drop all the way to 0, indicating that over the observation period, everyone had the event at some point. Another, and that's the Kaplan-Meier curve, by the way, which is representing kind of the chances of surviving past a certain time point. The hazard function is different. It's a function of survival, but it does a better job of conveying instantaneous risk. So not what are your chances of surviving 5 years, 10 years, 20 years, 2 months, 5 months, 7 months, but what are your chances? If you live a year, what are your chances of dying at 12 months? That's the hazard function. So this does look a little bit like the function from before, but now rather than the height representing your chances of surviving up to that point. So for instance, if you have a living donor, your chances of surviving to 2 years are approximately 99.5%. Assuming that you survived up to that point, 99.5%, that's the chance. The hazard function tells you your instantaneous risk of the event, assuming that you're living up to a year. So let's suppose along the x-axis, we have time, just as before. And the y-axis is actually, it's a probability, but it's a risk measure now. So for this particular event, let's call it death in this population, the risk is highest when? Early, right? In this population, your risk is highest early, and it's decreasing over time, which says if you can just survive early, your chances of death decrease greatly over time. So if I can think about this, maybe think about premature birth is really, really small infants. If you can get them past a certain point, then their chances of survival are really high. And so that certain point is kind of represented on this figure here. Their risk of death is highest kind of early. So again, this is defined as the probability of having the event during a very small time interval, assuming that individual survived up to that time point. And that's also called the conditional failure rate. It's very useful. I think you see the hazard function represented more in population health type studies as opposed to clinical studies, but it might also be informative for clinical studies. The hazard functions can behave differently. They don't look like the survival function always either stays high or it drops. The hazard function can increase and decrease, up and down as a function of when risk is highest and lowest. So depending on what disease you're looking at, what condition you're looking at, what the event is, you might have the blue line where the risk is high early, it levels off after a period of time, and then it increases again late. I'm trying to think of an example of that. Maybe just life, I don't know. I guess life would be wear out failures, right? Wear out failures. The risk of dying early is not very high, and then eventually we wear out. So our risk increases over time. This is the early infant mortality failure that I talked about, and it looks like the figure from the last slide where it's higher early on. If you can get them past a certain point, then the risk is reduced greatly and flattens out to near zero. And then you also might have what are called random failures, constant failures where the line is straight. So the risk never changes. And we do make assumptions when we do survival analyses about not necessarily what the hazard is for an individual treatment, but if we're comparing treatments, we make an assumption about the relationship between the hazards of those 2 treatments or 3 treatments or 5 treatments. How do we interpret the hazards? So the survival probability is pretty straightforward, right? What are your chances of living to a certain period of a certain point in time? The hazard's a little bit harder because it's trying to convey instantaneous risk. And I mentioned that the hazard function is probably more applicable in a public health study because it does a really good job of describing risk of something happening over a period of time. So if I calculate the hazard, suppose I'm doing a public health study, and I calculate the hazard, a statistic for contracting influenza, and the time measurement for my calculation was in months from this data. So I have information over a period of time in a population of who got the flu and when they got it, where time is measured in months. And let's suppose I calculate that hazard to be 0.015. What does that mean? Well, first of all, this is an average. This is an average. We're assuming the green line, even though the green line might not be true. It might be seasonal. But we're assuming that the hazard is constant and getting kind of an average hazard rate. The interpretation is that you would expect to contract the flu 0.015 times over the course of a month because time is measured in months. But that's meaningless unless I multiply it out to something that's more meaningful. So I can multiply the hazard by 12 to go from a month to a year. I can multiply that by 10 to go out to a decade. And that gives kind of an average risk of contracting the flu over 10 years. But it quantifies it not just in the chances of it happening, but how often can I expect it to happen? And so it turns out if I multiply that 0.015 by 12 and then again by 10 to scale it up to 10 years, the interpretation is much easier. It's basically you can expect, if that hazard is constant, to contract the flu twice in 10 years. And again, that's assuming, making the assumption of that green line, which might not be true. Cumulative hazard, we are at time, but I'm going to go ahead and finish. If you need to leave, I will not be offended. Just go ahead and go. I've only got like 2 more slides. the cumulative hazard describes how events are accumulating over time. So it's almost the inverse here of survival. And it's telling, conveying to the reader what fraction, if you will, of the population has had the event by a certain time. So the time axis is the same, and this is the cumulative fraction of the population who has experienced epilepsy by that time point. So, for instance, I've got 3 groups here: those receiving depression treatment, those who have depression but no treatment, and those who have no depression. And if I look at 8,000 days, I can see by 8,000 days, individuals with no depression in this study, less than 5% of them had experienced epilepsy by 8,000 days, compared to 7.5% who had depression, compared to 16 to 17% who received treatment for their depression. So the greater the value at a particular time, the greater the risk of that event by that time. How do we compare survival, though? So we've already talked about using Kaplan-Meier and hazards to describe survival and patterns of survival. To compare them, just like we have other measures of association, the hazard ratio is one that we use to compare survival patterns between groups. So you often see this reported, comparing groups with a confidence interval. And this represents how much more or less likely the event is to occur in one group relative to the control. But the kicker here is there's a time component to it. So if I have a hazard ratio of 1.1, the interpretation that you could take away from this is that the rate of the event, so rate conveys kind of time, right, as opposed to risk. The rate of the event is 10% higher during the observation period in the treatment group relative to the control. You could also think of it as, if we knew the window of measurement, which I don't for this, I don't know the day, if it's in days or if it's how long they observed it. You could also talk about the event occurs 10%, hold on, I had it in my head, just a second. 10% more events are happening over that window of time in the treatment group relative to the control. So you have a 10% increase in the events. That really didn't do a good job. I had it in my brain, then it was gone. But just know it's similar to an odds ratio in that it's conveying kind of increased risk, but also more the rate of the event than anything. To compare the survival functions between groups using a statistical method. So this is kind of an effect size. This is what you would convey how large the effect is. To do a statistical test, you could do a couple of different things. Probably the most common is the log rank test. The log rank test is actually it's addressing the question, are the survival functions for 2 groups different at any time? So if they're different early, they're different late, they're different in the middle, are they different anywhere? Or are they the same everywhere? There's problems with the log rank test in terms of its power to detect certain patterns of differences that we'll talk about a little bit next time. So you can see here on the left, there's a big difference between these 2 survival functions that's sustained over time. They never come back together. So that p-value from the log rank test is very small. However, here you do see a separation of the curves, but they're close together early, they separate, and they come back together. The log rank test will not detect this pattern of difference. You have to find something that's a more powerful or sensitive test to that kind of relationship. Cox regression models are just like linear regression models. They allow you to compare survival patterns between groups while adjusting for other factors. So there might be confounders or other sources of variation that need to be accounted for in the analysis, and Cox regression will allow you to do that. There are some very strict assumptions behind Cox regression that revolve around the hazards. We do have an example of that next time. And finally, the nice thing about survival analysis is it allows you to formally incorporate changing exposures over time or changing treatments over time through something called a time-varying covariate. So suppose you have a study where you're evaluating the effect of taking oral contraceptives on stress fracture risk in women athletes over 2 years. But you're doing it in an observational way where you're just asking individuals about their oral contraceptive use as opposed to randomly assigning them to use it or not, because that's not really ethical, right? Problem is, women switch on and off of oral contraceptives. So if you only ask them about their contraceptive use at baseline, then you might actually miss the true or a valid effect of its impact on stress fracture risk. But if you can actually ask them over time at repeated intervals, whether they're using or not, you can incorporate that change in exposure and get a more valid estimate of the impact of oral contraceptive use on stress fracture risk. And you do that using survival analysis. You basically turn on and turn off the exposure, and it's very easily done. And so you can see why this is a powerful tool. You can also compare median survival. So rather than just comparing the survival functions between two groups, maybe you're interested more in our patients. Is their median survival changing? Is it different? You can estimate it using the Kaplan-Meier function. There are also specific inferential tools that will allow you to compare the medians. But the median is very easy to visualize on a Kaplan-Meier curve. It's just the time at which the curve drops below 50%. The problem is there are some circumstances where the curves never drop below 50%, and so you can't ever estimate the average, the median survival time. So in summary, and we'll talk again a little bit more about this next week when we get into regression methods, the term survival analysis is used to refer to any method that assesses both the occurrence and timing of an event, and we tend to describe that kind of outcome using the different statistics that I talked about today in terms of the survival function, the hazard function, hazard ratios measure association, overall survival measures more did the event occur or not over a particular window of time. And we can also compare survival patterns between groups using things like the Kaplan-Meier curve that visualize survival, log rank tests which provide the inferences on whether survival is different, and Cox regression. They all incorporate that unique missing data called censoring, but they do have assumptions that have to be met, in particular Cox regression. And finally, the final point is that survival analyses extend beyond death. So any event of interest, as long as you have a well-defined origin point, a meaningful origin point, can be analyzed using these tools. Next time, we're going to continue to extend the idea of accounting for different sources of variation using regression, linear regression, logistic regression, survival, regression for survival methods, pulling examples from the literature. And then we're also going to spend a little bit of time to talk about power and sample size estimation, because I do get that question a lot, and I think it's important to at least address it in the context of a few very simple studies. Any questions? I apologize for going over, but I talked a lot. You didn't talk, I talked. Okay, if you have not received course materials, please do shoot me an email. You can come up and give me your email afterwards. I know that there were people that did not register prior to the first day who probably have not received the email. And I will also, at the end of, after next week, I will send out an email with the course materials one more time, and also a link to all the videos that will be uploaded onto YouTube, and an evaluation form. If you'd take 30 seconds to fill it out, tell us what worked, what didn't, what methods maybe we're missing or concepts we're missing. That way we can make modifications and improve the course for next year. I would appreciate it. All right, you guys have a great weekend.